Okay, welcome back after lunch. I'll just have a brief introduction to the speakers. I'm David Hobbs from Lund here. And today we have the pleasure of welcoming Laura Kreidberg from the Harvard Smithsonian Center for Astrophysics. And she has an impressive title of a junior fellow of the Harvard Society of Fellows and a fellow of the Institute for Theory and Computation in Harvard. And Laura today is going to tell us about the present and future of exoplanet atmosphere characterization, importantly from space. Thank you.
Thank you. Well, thank you everyone for inviting me. It's really a pleasure to be here, especially now that it's closer to the time I should be awake. And I wanted to also especially thank Sarah and Stéphane for the really thorough introduction to the field of exoplanets this morning. It makes my job a lot easier to talk about one of the big next steps in the study of exoplanets, which is characterization of their atmospheres. Let me put my slides on. Thank you. All right, there we go. Okay. Yes, so I really like this tweet. It's a quote from Jill Tarter at a recent WAST meeting where she said, "We can now say with statistical certainty that there are more planets than stars in the galaxy." And this is just an amazing fact that we know this. This is something we didn't even know when I was starting grad school not that long ago. And we've made enormous progress just in the last couple of decades in the discovery of planets outside the solar system. And we've seen, as we heard this morning, a huge diversity of systems. Systems very, very different from our own solar system. You can see this is just a plot of pure detections, not corrected for any kind of survey sensitivity. But you see all of these planets interior to the orbit of the solar system planets, planets in between the size of the Earth and our ice giants, Uranus and Neptune, so it's really interesting to see what those are. And we can make great inroads into studying how these planets form and evolve just by looking at their current orbital architectures, measuring their masses and radii. But the focus of my work is to study the atmospheres of the planets. And we do this for a couple of reasons. We can gain a lot of insight into how the planets form, how their atmospheres change over time, and also answer the question simply, what are they like, by studying the atmospheres. In the case of gas giant planets like Jupiter, the composition of the atmosphere provides a record of the conditions in the protoplanetary disk where the planet forms. So we think we have a core of the planet that sweeps up surrounding gas and dust and planetesimals. And so by studying the present day atmospheric composition of the planets, we can learn about the disk conditions, the location where the planet formed in the disk. And for smaller planets, we already know from our solar system that a vast diversity of atmospheres can exist. These are formed from secondary processes like outgassing due to volcanism. We think they've lost their primordial hydrogen envelopes. And so if we're interested in the question of habitability, we absolutely have to study the atmospheres. So I wanted to give just a little bit of overview of how we actually do this. When I started graduate school, I thought, surely we cannot learn about the atmospheres of planets that are hundreds of parsecs away from us. That sounds just too hard. It turns out it is very hard, but it is possible. And so one technique that we use is called transmission spectroscopy. And the idea here is that as the planet transits in front of its parent star, a small fraction of the stellar light will filter through the planetary atmosphere. And depending on the opacity of the atmosphere at a given wavelength, the planet's apparent size, its transit depth, can increase or decrease. So the planet appears larger when the atmosphere is more opaque. The amplitude of this effect is sensitive to a couple of things. The larger the planet is relative to your star, the easier job you'll have. And so planets around small stars are particularly attractive candidates for this kind of characterization. And it's also sensitive to the scale height of the atmosphere. So if you remember from when you learned hydrostatic equilibrium, the scale height is the distance over which the pressure drops by a factor of E. And that's related to the temperature of the atmosphere, the surface gravity, and also the mean molecular weight. So our best case scenario here is a very hot gas giant planet with an atmosphere dominated by hydrogen and helium orbiting a small star. And in that case, best case scenario, the amplitude of these features, so from bottom to top, is about 0.1%. So very small, and can be orders of magnitude smaller than that for an Earth-like planet. And just to give a real illustration of how this works, I love this. Let's see if it'll go. So here's an image of the Earth. Now here, that was going really fast. All right. So 8.6 versus 9.6 microns shows you the continuum versus the ozone band. And you can see that the planet is noticeably bigger in the ozone band. And so the goal eventually in this field is to look for signatures like that in the atmospheres of extrasolar planets. A second technique that we use is called emission spectroscopy. This is a corollary to the transmission spectroscopy technique. And the idea here is that if you can observe a full orbit of a planet, you assume it's tidally locked, so there's a hot side and a cold side. And depending on the viewing geometry, you can get the full disk of the planet. Then in secondary eclipse, you have a baseline measurement of the stellar flux alone. And then here you have the hot day side rotating out of view. And so by measuring the differential flux relative to this baseline here that gives you the star by itself, you can measure the ratio of planet to star flux over time and learn both the thermal emission or reflected light component from the planet as it varies with orbital phase. And so you can actually gain spatial information as well. And just as before with the transmission spectroscopy case, your best scenario will give you a signal amplitude of order 0.1%. So I like to say that we are currently experiencing a watershed moment for exoplanet atmospheres. And I feel like normally this is the kind of hyperbolic statement that you would put in observing proposals, but in this case I actually really believe that it's true for a couple reasons. One of them is that, as we heard this morning, we are poised to detect thousands more planets around the very brightest and nearest stars. This is a picture of TESS right before it launched. And both by ground-based, space-based surveys and radial velocity surveys from the ground, we'll be able to measure the masses and radii of as complete a census of the nearby exoplanet population as we can hope to. And these will be the planets whose atmospheres we can then go and characterize. The second reason I think that this is a watershed moment for exoplanet atmospheres is that JWST is launching soon. I didn't put a date on there because I didn't want to jinx it. The last time I gave this talk was actually the day the first launch delay was announced, so I'm taking the dates off. But I like to say that JWST is going to be 10,000 times better than Hubble for this atmospheric characterization work. Hubble already gives us a huge advantage because it's very stable. It allows us to probe wavelengths that are inaccessible from the ground, in particular the UV and in the water bands. And we're free from the turbulence introduced by the Earth's atmosphere, and it enables us to make very precise measurements. JWST will be much, much better again, thanks to about a factor of 10 increase in collecting area, which gives us more photons that we need to detect these tiny, tiny signals. It also has much better wavelength coverage, so it extends from the optical all the way into the infrared. We can get spectroscopic coverage all the way out to 12 microns, which is important because it gives access to more molecular features. We can see features from methane, from ammonia, from CO2, CO, in addition to the water features we already can see. And it also allows us to make thermal emission measurements for cooler objects. So if you're looking at a planet that's 500 Kelvin, you need to go into the infrared to be able to see it relative to the star. So the way I organized my talk is by planet size. I'm going to start with big planets and move my way to small planets. And I'll talk about current work that's ongoing to characterize their atmospheres, and then I'll also try to make the connection to what we plan to do in the near future. Okay, so questions for big planets. They're fairly simple at present. We want to know, what are they made of? What atoms and what molecules are present in their atmospheres? What are the absolute abundances? and abundance ratios of those species, and how does that connect back to the conditions where the planets were forming. We also want to know what their climates are like. Some of these Jupiter-sized planets are in very exotic orbits compared to the solar system. We're mainly looking at planets with orbital periods less than about 3 days. We expect them to be tidally locked, so you have a tremendously irradiated object with a short rotation period. And what does that do to the climate of the planet, to its atmospheric circulation? And finally, we want to know whether these planets have clouds or hazes in their atmospheres. We know that all of the planets, all of the bodies in the solar system that have substantial atmospheres have some kinds of clouds or haze. And so that has important ramifications for what we can learn about the atmospheres from far away. So just a couple of expectations for what the composition of a giant planet atmosphere should be like. Here's Jupiter. You see all of the beautiful colors and structures. What you don't see is actually the primary constituents of the atmosphere, which are hydrogen and helium. There are ammonia clouds deep in the atmosphere, and then there's beautiful reddish-brown cloud patterns we think are due to tholins, these sort of hydrocarbon-like hazes whose composition is still relatively unknown. And so to get an idea of what the spectrum of a giant planet atmosphere might be like, you could take a solar composition gas, which we think to first order is a reasonable approximation for the composition, and put it at the temperature and pressure of a planet. So in this case, this is a fairly typical hot Jupiter with a temperature of 1500 Kelvin, looking at a pressure of about a bar. And the colors correspond to different spectral features from different molecules. I'm sorry, that's kind of small. And more strongly absorbing is up. And so you can see in blue, there's all of these water absorption features. You have some CO poking out around 5 microns. This is potassium here. Off to the left, off the x-axis, is the sodium line, which is very strong. So all of these things are what we would reasonably expect to see in the atmosphere of a hot Jupiter if it in fact has a composition fairly similar to the sun. And excitingly, this is exactly what we saw. So this is the very, very first detection of an extrasolar planet atmosphere from Dave Charbonneau in 2002. This is from STIS on the Hubble Space Telescope. And you can see very clearly a strong absorption feature coinciding with the sodium line. And so this was really exciting, and it carried the field forward for a long time. But there's a big difference between simply detecting a molecule that we expected to be there and actually measuring its abundance. And that is something that didn't start to really happen until more than a decade later. And so I'm skipping about 10 years of intermittent progress here to get us to the present, which is focused mainly on water. And thanks to the installation of the Wide Field Camera 3 detector in 2009, this is the most recent instrument installed on HST, we're able to observe features in the water band at a level of precision and robustness that has never been possible before. And it's thanks to a couple of different things. So one is that the folks at Space Telescope have implemented a really novel observing strategy for us, which is called spatial scanning. And the idea here is that, so HST was not designed to look at very nearby bright stars. It was designed for some reason to look at faint distant galaxies. And so most of the stars that host the planets we can study are too bright for normal observing modes on Hubble. And so what they do for us is they do a scan in the spatial direction. So dispersion direction is left to right, spatial direction is top to bottom. And this is one exposure, and they smear the light out over the full extent of the detector, and it enables you to observe brighter targets with a good duty cycle that would otherwise be completely inaccessible. It also spreads the light out over more pixels, and so you average over the sensitivity variations on the detector. At the level of precision we want, if you have one pixel that is slightly less sensitive and not perfectly corrected by your flat field, that actually messes up your result. And was responsible for actually a lot of spurious detections through the mid-2000s. But thanks to Wide Field Camera 3, WFC3, we get these beautiful, very precise, highly repeatable transit observations. And you can see this one. I've color-coded 3 different visits, and you can't distinguish between them. You get completely consistent results every time, and this has been repeated by many different groups, so we're really confident that the results we're getting are reliable. And of course, as soon as this became available, we detected water in a whole bunch of extrasolar planet atmospheres. So this was, I think this was the first one. This is the Hot Jupiter HD 209458b. Here's another one. There were 5 or 6 just in 2013 when this first became available. And moving forward from this, we said, okay, great. We're seeing the water. It looks exactly like what we thought. The next question is, can you measure how much water is actually there? And so this is work that I led as a graduate student. These are spectra for the Hot Jupiter WAST 43b. And we measured both the thermal emission and the transmission spectrum for this planet. And in both cases, you can see a really nice water absorption feature. So right there. And here's the transmission spectrum. And remember that absorption is up because the planet looks bigger when the atmosphere is more opaque. And we retrieved the atmospheric composition. We basically did a giant Monte Carlo simulation where we varied the temperature pressure profile and the composition, the abundance of different species in the atmosphere to see which models reproduced the features that we saw. And the results of that I'm showing on the right here. The dotted line shows constraints from the transmission spectrum, the bottom plot, and the dashed line is from the emission spectrum. And these are effectively 2 independent measurements of the water abundance. We're using 2 different data sets observed in different regions of the planet's atmosphere, which we assume to first order have the same composition. So we were heartened by this, and we combined the measurements into a joint constraint on the water, which is about 1/2 to 3.5 times solar. And when I say solar composition, solar abundance of water, what I mean is you take a solar composition gas and you cool it off to the temperature of the planet. And so this was really exciting because it was a precise enough measurement to provide meaningful comparison with the solar system planets for the first time. So this is a well-known solar system trend of decreasing atmospheric metallicity with increasing planet mass. We think that the reason this exists is that the lower mass planets have a smaller hydrogen-helium envelope, and when they're impacted by planetesimals during the formation stage, the atmosphere is relatively more polluted. We use methane as a proxy for metallicity in the solar system planets. It's actually very, very challenging to measure their water abundance directly because they're so cold that water has condensed out of the observable parts of their atmospheres. And then for WAST 43b, we used our beautiful measurement of the water abundance as a proxy for metallicity. And we were really excited to see that our measurement falls right along the trend seen for the solar system. To give you a sense of what we can look forward to with JWST, these are simulated observations for another hot Jupiter. For a proposal that was accepted as part of the JWST early release science program. This is an 80-hour program with about 100 collaborators. This was definitely the biggest project I have ever worked on. The telecons were long. And you can see that just with a single transit with each instrument, you can get beautiful precision on all of these different molecular features, and then retrieve the atmospheric composition, both the metallicity and the ratio of carbon to oxygen, which is a sensitive test of where in the disk the planet formed, all with a single transit observation for a fairly typical object. So we are waiting with bated breath to see if it actually turns out to look like this. But of course, we're only going to be able to observe a limited number of planetary atmospheres with JWST because the time is simply so precious. And so I used to give this slide and I would say we need a dedicated atmosphere characterization mission, but excitingly, one was just approved. So Ariel was recently selected by ESA to launch in 2028. And the goal of this mission is to determine the atmospheric composition for a large statistical sample of exoplanets, 500 to 1,000, to measure these trends, to try to measure how the atmospheric metallicity changes as a function of planet mass, that are predicted by planet population synthesis models, and begin to tune the model parameters to say how big are the planetesimals, where in the disk are the planets forming, what is the surface density of solids, what is the accretion rate of gas versus solids as the planets are growing. And so this is another thing we can look forward to in the relatively near future. Okay, I want to change gears a little bit and talk about climate instead of composition. So one of the other things we really want to know about these planets is what their climates are like today. In particular, what is the temperature at a given latitude, longitude, and altitude? Can we take an object that is not spatially resolved from its host star and actually figure this out? So the first attempt at this was secondary eclipse observations of HD 209458b, the very first planet detected in transit. And these were done with the Spitzer Space Telescope, and they were really interesting. So they measured the planet-to-star flux ratio at a number of different photometric bands. And I've circled the data points. There's a lot going on here, but the things to pay attention to are the blue and the red circles. And you can see down here at 3.5, 8 microns, and out here past 20, the data points all agree reasonably well with this black body. It's 1500 Kelvin. These points, the red points, agree much better with a hotter black body temperature, about 1900 Kelvin. And this is interesting because these points are in a region of wavelength range with higher opacity. And if you're looking at higher opacity wavelengths, you can't see as deep in the atmosphere, so you're probing higher altitudes. And the thinking here is that up here at these higher altitudes, the temperature of the atmosphere is actually higher. And so there was an inference that this planet has a stratosphere, much like the stratosphere on Earth. So we know in Earth's atmosphere, ozone is very strongly absorbing of optical light, and so it heats up the atmosphere and creates a thermal inversion layer where it's actually hotter as you go higher in altitude rather than cooling off. And there are a couple plausible candidates for what could cause a thermal inversion in the atmosphere of one of these hot planets. It's much too hot for ozone to exist, but more exotic species like titanium and vanadium oxide have been theorized to exist in the atmospheres. And as you know, if you've worn sunscreen, titanium oxide is a really strong absorber of UV light, and so it could create a strong thermal inversion like this. However, as time went on, this result actually did not hold up. And this gives you a sort of historical sense of how our understanding of these atmospheres has changed over time as our data analysis techniques have gotten much better. Because Spitzer, just like Hubble, was not designed to make measurements at this level of precision. And so as our analysis techniques have gotten better, we've revised the measurements that were originally made. And so this is the most recent analysis of the data, showing, in fact, that these two high points up here have moved down and are now consistent with a non-inverted temperature-pressure profile. So the red is the new result, showing, just as you would expect, the temperature increases as you go deeper in the atmosphere. This was confirmed with HST, where we actually resolve a spectral feature. This is a feature from water, and you can see that this dip right here, this is an absorption feature, not an emission feature. So I thought I would talk a little bit about how this has proceeded into the present day. This is a paper of mine that was actually just accepted last week, I think. And it's the same idea. We wanted to measure the temperature-pressure profile, so how the temperature is changing with altitude, over the entire phase space for the planet. So at every longitude, we wanted to measure what the climate is like. And so we observed a thermal phase curve of the planet. And this is amazing to me. This looks just like the cartoon I showed at the beginning. You see the hot day side of the planet rotating into view here. This is the secondary eclipse, not the transit. And then the day side rotates back out of view. And we did this, we have spectroscopy between 1.1 and 1.7 microns targeting water. And then we also have Spitzer photometry at 3 and 4 microns. And so the first question that I asked with this data set is how well you can actually figure out the climate of the planet, how well you can take a disk-integrated average of the planet brightness and work backwards to figure out what the temperature is at any given latitude and longitude. And so I worked with a graduate student at the time, Tom Loudon. We wrote a Python package called SpiderMan that will take any temperature map for a planet and convert it into a phase curve very quickly so that you can run an MCMC. And we decided first to do the very simplest thing, to say, suppose you use spherical harmonics, so take all the physics out of what you expect the temperature to be like. And that gives you a pretty good fit. Looks like the data are matched really well. But then we found there's other models that can give very similar fits. So this one was a physically motivated model where you essentially say, all right, take a parcel of gas. On the day side, you heat it up and it can advect around with a constant wind velocity. And with just 3 free parameters, you can get temperature maps that reproduce pretty closely what you would get from a 3D GCM simulation. And this also gives you a pretty good fit, but you'll notice that there are pretty big differences. So the substellar point is almost 1,000 Kelvin hotter in this case than in this one. We also found that if you make the dumbest model possible that has just a day-side temperature and a night-side temperature, you can get a pretty good fit as well. And finally, we compared to a real 3D simulation, a GCM, that had as much physics and chemistry put in as possible, radiative transfer coupled to the atmospheric dynamics. And that gives us a pretty good fit too. So I would say that this is where we stand now. We can get some temperature information out, but with the current level of precision of the data, even what we can get with Hubble observations of the highest signal-to-noise systems, it's still really hard to uniquely identify what the climate of these planets is like. But one thing that we did get to see for this system is that the thermal inversion is back. So this is the day-side spectrum. So you're looking represents the substellar point. So this is when the planet goes behind the star. And you can see that in the 1 to 2 micron range, the data agree really well with the black body. That was weird because that's, if you remember, where we were seeing water absorption features before. And so the question is, where is the water? And what we finally realized is that this planet is so hot that the water is dissociating. And it's different from M dwarfs. So the planet is so hot, it's the same temperature as a mid to late type M dwarf. And you definitely see water absorption features in stars that are that cool. And the difference here is that the surface gravity is a lot lower, and so you're probing higher up in the photosphere where it's easier for the water to dissociate. However, what does not dissociate as easily is CO. And we see a really big CO feature right here at 4.5 microns. And just as before with HT209458b, or at least as we initially thought, this feature is seen in emission, so it's hotter as you're probing these higher opacity windows. And so we think that the temperature actually increases with altitude, at least on the day side. On the other hand, because we have a phase curve, we can look at the spectrum at different phases. And this is as close to the night side as you can get. So this is right before the transit. And you can see the Hubble data, again, look like a black body. But then at the Spitzer wavelengths, the planet is actually cooler. And what we think is happening is that you would expect a thermal inversion to happen on the day side because there's a heat source from high up. The star is irradiating the planet there. And so if you have some kind of optical absorber like TiO or VO or even sodium, that'll heat up the upper layer. But on the night side, there's no heat source. And so you wouldn't expect a thermal inversion there. And in fact, that's exactly what we see, is that the thermal structure is changing with longitude, which I think is amazing that we can measure that for something that we can't resolve that is so far away. And you can see, if you look at all the phases, this 4.5 micron feature transitions from being an absorption on the night side around to the day side where you see it in emission and then back around. Okay, so in the future, JWST is going to give us huge advantages for doing phase curve observations of cooler objects, since we can go out to longer wavelengths. And one of the other components of this early release science program that was recently approved is a phase curve observation of a hot Jupiter called WAST 43b. And I, along with Nicolas Cruzet, are leading this component of the observations. And the plan is to observe a full, roughly 24-hour orbit of the planet in the infrared with MIRIs, so 5 to 12 micron observation. And one of the things we really want to look at is the chemistry on the night side. So this is a prediction of the night side thermal emission spectrum of the planet, and as you can see, it's shaped pretty closely by clouds of different species, and we think that it's so much hotter on the day side than the night side that you can get clouds condensing on the night side and potentially advecting around. And so we need the full phase information to understand how the chemistry and climate are changing in order to interpret these other observations that are snapshots of single regions of the atmosphere. Another thing we can do is do what's called an eclipse map of the planet. So as the planet is moving behind the star, the different slices of it are being eclipsed at a given time. And so if you have really precise data, you can work out what the brightness temperature of each slice is as the planet is being sequentially eclipsed by the star. And so that's what this would look like. So this is the difference in the flux for a realistic temperature map for the day side as compared to a uniform disk. And so that'll fix our degeneracy that we had earlier, where there were all of those different temperature maps that we could reproduce the phase curve. By looking at this ingress and egress shape, you can figure out in great detail what the brightness distribution on the surface is. And it gives you latitude as well as longitude information. So that's something that will be really, really cool that has only barely been possible so far. Okay. I'll talk very briefly about clouds and hazes. I'm going to come back to this. Clouds and hazes exist. It was one of the earliest robust detections in an exoplanet atmosphere. This is for another hot Jupiter, HD 189733b. And the expectation was this black curve. We thought there would be these beautiful big features. In reality, what was seen is this. This is consistent with what you would expect for scattering off of haze particles. And it was seen again in HG 209458b in a slightly different way. This is the wavelength where you'd expect water absorption features. And there is indeed this water absorption feature, but it's a lot smaller than what was expected. This is about 1 scale height in the atmosphere. That's where the pressure is dropping by a factor of E. And in a cloud-free atmosphere at this spectral resolution, you would expect to cross about 3 scale heights. And so the features are muted in amplitude by about 60 or 70%. The interpretation is that if you put a cloud deck at fairly high altitudes, you truncate the absorption feature because the stellar light can't pass through the cloud. And if you put together the ensemble of all of the high precision space-based hot Jupiter observations to date, this is work by David Singh, you can see a whole continuum of feature sizes. So you get everything from this large water feature here to very, very flat spectra. And so far, at least for the hot Jupiters, it's been tough to identify any kind of physical mechanism that is causing the difference, whether it's the temperature, the planet mass, or the irradiation, or what. And so I think that remains an open question that we'll be able to start addressing as we observe better spectra for more systems. I'll say also just a couple words about atmospheric evolution. We know that especially in the early lifetimes of planets, the stars are very bright in the UV, and that can photoevaporate a lot of the atmosphere. We think that may have been partially responsible for why Mars lost its atmosphere. And indeed, planets have been caught in the act of evaporating. So this is a transit observation in the Lyman alpha line of another hot Jupiter, and you can see this right here is where the transit is. These are big error bars because the Lyman alpha flux of the star is faint because it's far away. But you can see that the planet's transit depth is about 10%. So this is 0.9 right here, as opposed to roughly 1% at other wavelengths. And so that suggests an enormous cloud of evaporating hydrogen. Really excitingly, this result was just, I think, 2 weeks ago. A new probe for atmospheric escape was finally shown to work. So all the previous observations were done in the ultraviolet, which, as Stéphane alluded to earlier, is capability that will be lost when HST stops operating. But Jessica Spake recently discovered an evaporating exosphere in a hot Neptune, WAST 107b, looking at an excited helium line at 1083 nanometers. This was first predicted way back in 2000 by Sarah Seeger and was not seen until just this past year. So this is really exciting because it's the only signature of evaporation that isn't in the UV. And so this is something that is possible not only with James Webb, but also with ground-based facilities. And so we'll have a new window into atmospheric escape for the coming years. All right, I am running out of time, so I'll transition now to talk a little bit about medium-sized planets. And for medium-sized planets, we have many of the same questions as we have for gas giants. What are they made out of? What are their climates like? Also, how are they different from gas giants? What stunted their growth? Why are they not Jupiter-like? And is there anything we can learn about their formation process from their atmospheres today? And when I say medium planets, I'm really referring to this population here, which is an important one. So this is recent work from B.J. Fulton showing the radius distribution of planets from Kepler. I'm sure you guys have all seen this. And this is the occurrence rate of planets with orbits less than 100 days. And you can see that planets in this roughly 2.5 Earth radius regime are among the most abundant in the galaxy. It's really weird that our solar system doesn't have one. We have Earth with 1 Earth radius, and Neptune is the next closest, I think, and that's closer to 4 Earth radii. So we really want to know what these things are. And as we heard from Sarah and Stéphane, the mass and radius measurements of these planets show a lot of diversity in their bulk compositions. And indeed, that is expected from planet population synthesis models. So this is the predicted atmospheric metallicity as a function of planet mass. The different colors correspond to different assumptions about the planetesimal population. But you can see that these smaller planets are expected to be more metal enriched, because if you have a smaller hydrogen envelope and a planetesimal comes in there, it'll pollute it relatively more. And there's also a huge amount of scatter. So this is something we want to actually go out and measure. Unfortunately, the target list is very short. If you remember, the amplitude of features is directly proportional to the planet radius. And so if your planet radius goes down by a factor of 4, your signal size goes down by a factor of, or your signal to noise goes down by a factor of 16. So there's only a handful of these objects that are accessible now. Everybody's favorite for a long time has been GJ1214b. This is a 2.7 Earth radius planet orbiting a very small star, a nearby M dwarf that's only 20% the radius of the Sun. And the transmission spectrum, as of 2013, was very flat. But there were two possible explanations for this. One is that it had a high mean molecular weight composition, as you might expect if your atmosphere is very enriched by water-rich planetesimals falling in. Or it could have high-altitude clouds, and the data as of 2013 were not precise enough to tell the difference. And so one of the projects I worked on in grad school is this very, very, very precise measurement of the planet's transmission spectrum. This was, at the time, a record allocation of Hubble orbits for studying a single exoplanetary system. We observed 15 transits. It was 60 orbits of HST time. And it's still flat. which was not what we were hoping, but that's what nature has given us. But the nice thing about this is that it was so flat that we were able to rule out at high confidence all high mean molecular weight atmospheric composition. So even if you made the atmosphere out of pure CO2, our observations are so sensitive that we would have detected that. And this was, for a long time after this, we kept proposing for more time to observe similar planets, and the TAC would come back and they would say, no, like you already know they're all going to be flat, why are you doing this? But after years and years of chipping away at it, this is the current picture of what these smaller planets are like. So here's all 6 of them. These are all observed with Wide Field Camera 3 on Hubble. I've standardized them I normalized by the atmospheric scale height, so they're all on the same axis. And I sorted them by color. And you can see that there's, or by temperature, sorry. And you can see that there's a range. Some of them, like HAT 26, have really nice, high signal-to-noise water features. GJ1214b is flat as a pancake. There actually are error bars on this, you just can't see them because they're smaller than the points. And so with Ian Crossfield, we looked at this and we said, okay, as soon as you have 6 planets, that's enough of a sample to do a population study. So we tried to see whether there were any physical parameters that were correlated with the amplitude of this water feature. And one of the things we found is that the hotter planets tend to have larger features. So the y-axis is the water feature amplitude and scale heights. And x-axis is temperature, and you can see that the hotter ones do have larger features. It's possible that rather than a line, this might be more of a step function because we expect photochemical hazes to start becoming abundant at temperatures below 800 Kelvin or so. That's where methane becomes the dominant carrier of carbon. If you have methane and ultraviolet light, it's very easy to break up that methane and recombine it into chains of hydrocarbons and get these photochemical hazes that are commonly seen in the solar system. We see these in Jupiter, Saturn, even in Pluto's atmosphere. We very recently observed another planet in this mass range. This planet is WAST 107b, same planet that's evaporating in helium. And so we looked at this and we thought, oh, great, we predicted a trend in the amplitude of the water feature with temperature. How does this planet stack up on that trend? And there it is. We were so shocked. I felt like a theorist for the first time and made a prediction that actually worked. So far, now that we have 7 objects, our line is still holding up okay. And very excitingly, hundreds of planets in this size regime are expected to be discovered by TESS and other surveys that will be easily accessible with JWST. So hopefully we can make a lot of inroads into this question in years to come. Okay, in my last 5 or so minutes, I want to talk about small planets. So planets like the Earth, rocky planets that do not have hydrogen and helium atmospheres. If they have atmospheres at all, they were probably outgassed by volcanism, or you can have volatiles delivered by comets. And the same questions apply. We still want to know what they're made out of and what their climates are like. But in this case, we add a second question, which is, can any of them support life, especially life as we know it? So very excitingly, as you all know, we've had a plethora of detections of small planets around nearby small stars. You know that you've made it when Google Doodle features your result. This is from the TRAPPIST system detection, where there's 7 transiting planets. I identify with the moon in this. Yeah! All right. So in addition to the TRAPPIST planets, the MIRTH survey has also detected a planet around GJ 1132 and LHS 1140. So there's about 10 of these. A handful of them are in the canonical habitable zone, where the temperature might be appropriate for liquid water. However, there are a lot of questions about these planets. So even if you have a planet that is the same size and the same equilibrium temperature as the Earth, if you put it around a very small star, there's a key difference, which is that the orbital period is very short, roughly 10 days in contrast to a full year. And so you'd expect the planet to be tidally locked, so the atmosphere would be very different from the atmosphere on the Earth. The stars are also different. So M dwarfs, these smallest stars, have a long, early bright UV phase where they are contracting to the main sequence. They have more flares, more stellar wind. This is a plot from a paper of a student of mine that was just submitted showing the lifetime integrated X-ray flux as a function of stellar mass that a planet in the habitable zone would receive. And you can see that for a planet around an M dwarf, you would expect about 2 orders of magnitude more X-ray flux in the planet's lifetime, which all can contribute to the erosion and escape of the atmosphere. And if the planet is tidally locked, the atmosphere can also collapse on the night side. You can freeze it out and get what I like to call a snow cone planet, where it's ice on one side and rock on the other side. So the first question that I was interested in answering for these exciting new planet detections is whether the atmospheres are actually accessible for characterization or not. And so this is work that was led by Caroline Morley, where we used the solar system as inspiration for what range of atmospheric compositions are possible. And we said, okay, and they're influenced by all of these factors here, what volatiles are delivered, what the interior composition of the planet is, what the planet mass is, and how that affects the volcanism, how the atmosphere might have evolved over time under the influence of more UV radiation from the star, all of these things. And so we decided to be pretty agnostic and say, all right, suppose the atmospheres of these planets had compositions similar to the Earth, Titan, the moon of Saturn, and Venus. We looked at a range of pressures, and we painted on these atmospheres at the temperatures of the planets that have been discovered. And then we asked, can these atmospheres actually be detected? And so I simulated JWST observations with the Pandexo tool, and we made up some criteria for what constitutes a detection to see how many transits or eclipses you would need to actually make a robust measurement of the atmosphere. And this is what it looked like. So this is TRAPPIST-1b. This planet is a little bit hotter than the Earth. It's about 500 Kelvin equilibrium temperature. And our nominal model was a 1 bar Venus-like atmosphere. And you can see that with 9 eclipse observations and 6 transit observations, you can start to really make out these features. And excitingly, the features you would expect for different composition atmospheres are distinct from each other. So for a Venus-like composition, you're primarily seeing features from carbon dioxide. For an Earth-like composition, you see water. And for a Titan-like composition, you see methane. And so it's within reason to start making inroads into what the compositions of these terrestrial planet atmospheres are like with a fairly modest allocation of JWST time. You may be wondering whether I cherry-picked this example. The answer is yes, I did. So here's a giant table showing roughly how many transits or eclipses you would need. If there's a dash, that means you need more than 100. I've grayed out, so we looked at 2 different cases. We weren't sure exactly what the masses of some of the planets are. And as new information has come out, the right-hand column is more realistic. And so you can see that while a handful of these atmospheres are fairly accessible, the hotter planets you can get with I think 10 to 20 is a reasonable number of transits or eclipses to expect based on historical precedent with HST, maybe a few more than that since these are such important systems. But most of them are probably too hard. And so the point I want to leave you with is that we can look forward to very, very precise observations of exoplanet atmospheres, both with current facilities and with JWST in the near future. For gas giant planets, for ice giants, we will learn about their atmospheres in unprecedented detail, both in terms of their chemical composition and their climates. But if we really want to answer the question of habitability, whether there are planets like our Earth out there, and especially to look for biosignatures, we're still going to need next generation facilities. And I know there's a lot of students and postdocs in this room, so I want to speak to you specifically and say that this is our job, is to make sure that these facilities are built and are successful. And I think if we do that, we have a lot to look forward to as young people in this field. All right, thank you.
Okay, thank you, Laura. We will take questions from the audience. So the procedure is you get a microphone first, and then you state your name, and after that you can say anything you like. So, do we have any questions? Or I will ask a technical question if we don't get one.
Oops,
sorry.
Hi, Laura. My name is Matthias Schulig, and you showed this overview of hot Jupiter atmospheres from the Singh et al. Paper. And we see that there's hazy and also not very hazy atmospheres. So can we infer anything about upwelling in those atmospheres? So the material that forms the clouds, can we say it must come from deeper below? Because you stated that the atmospheric heights probed here are very, very high up.
Yeah, that's a great question. So I think that the answer is complicated in the sense that there are multiple different kinds of condensing species. You can have clouds condensing in chemical equilibrium like the water clouds in Earth's atmosphere, but you can also have these photochemical hazes that would be produced in situ by UV irradiation of the upper atmosphere. And so it's hard to say in the absence of information about what the clouds or hazes are actually composed of, whether they were formed that high or whether they were upwelling from deeper.
So we cannot really comment
yeah, I mean, you can say a little
high
bit more
molecular
like,
weight.
Yeah, I mean, you can say some things about, like, if the particles are too large, they'll sink. And so you can make some timescale arguments for what the particle size distribution can reasonably be to keep the stuff wafted that high. Yeah.
Yep.
Hello, my name is Brian Thorsbro. My question is, how confident are you in the model atmospheres for exoplanets? Is it a mature field, or is there still a lot of work to do in this?
That's a great question. I think that there's a number of limitations now. One big one is the line lists are incomplete. And so there's been a lot of great laboratory work to make sure the line lists are all complete and accurate. I think that the biggest theoretical challenge that remains is being able to have a self-consistent 3D model that can run fast enough to do an MCMC over. So if we've learned anything about planets in the last 5 years, it's that they're very complicated and 3D effects matter. And so most of the theoretical modeling now is done in one dimension. And what I would like to see in the future is a 3D simulation that you can iterate over and explore in an MCMC-like way, which I think would give you a much more robust estimate of what the abundances and the temperatures are actually like.
Okay, Ross has a question for you.
Ross Church. You gave a very good description of what we will be able to do with JWST. Could you contrast briefly what Ariel will be better at than JWST and what not?
Yeah, Ariel has one huge advantage, which is that it's a dedicated facility. And so the expectation is that there will be hundreds, if not 1,000 atmospheres characterized, whereas if history is any precedent, I would say with JWST we'll get 100 or so, maybe 200 if we're lucky, depending on the mission lifetime. And so it's just a numbers game. The data will not be as precise, and the wavelength coverage is more limited.
Mm-hmm. Okay, yeah, go ahead.
Okay, I will take the liberty to ask one also. So you show a very nice plot with the metallicity of the atmosphere as a function of the mass of the planet. I don't know if you can bring it back. You had some prediction on, and you had some plots. You were one of the first plots. Let's get a bit earlier.
Yep, here.
This one exactly. Now, one prediction I would absolutely make as a theory is that it's gonna flatten out around 1 at some point, because
Yes.
once you start to accrete gas that has just a kind of small dust in it, that's where it's gonna sit. So I wonder. Has it been done, or have people started thinking about doing this for 10 Jupiter mass objects? Because then you should really start to see solar metallicity. Otherwise, it would be a little bit hard to explain if it will follow that dash
Yeah,
line
no,
down, right?
this is an excellent question, and this is actually Christoph Morticini is very, very sneakily mentioned this, where he says gas dominated right here. And so I'm actually, this is one of my JWST proposals that I want to write, is looking at the composition of a 10 Jupiter mass thing as a pristine probe of the gas composition in the disk. Yeah, good question.
Okay, any other questions from the audience? I had one small, which is slightly technical question, but I really like this spatial scanning mode on the HST, but I would have thought that would cause problems when you're trying to make spectra, if it would decrease the resolution rather than enhance it.
It does cause problems. The scan rate varies a little bit, and you get some. It's not perfect, but we're binning the spectrum in such wide wavelength bins that it doesn't really degrade. So yeah, we're not close to the native resolution of the spectrograph.
Okay, and will this be used on James Webb also?
No.
No, they've designed it out in effect.
Yeah.
The need for it.
Yeah, and JWST will have much better pointing precision anyway, and so you'll be able to keep the spectrum on the same pixels, and so you won't be as worried about variation due to pointing moving around.
Okay, thank you. So if there are no more questions, nobody else, then we'll move on to the next speaker. Thank you very much, Laura.
Thank you.